Welcome to this recorded video that will be discussing the assignment for the third module that goes over functions, logic, a little bit of loops, and also the important topic of how to test your functions in modules. I'm expecting that it will take between 6 to 9 hours to complete this assignment. In this assignment, we use NumPy, so you should run this first code cell to make sure that you import NumPy as NP. The first problem involves population growth. This is a model and solution that you saw in the final activity of your 01 Jupyter lecture notebook. So you might want to review that to help you with this problem. In fact, if you did it correctly, you might just want to copy that material over. Otherwise, you might want to click on this link again. I'd recommend doing that anyways, and just refreshing yourself about this is what the differential equation is, and then here's what the solution is. And I would recommend just focusing on writing up this part of the solution. Ignore this part right here, the second part, that second form. Just this one. This will be easier to code up. So what I'm asking you to do is just in Markdown, this should be an easy part of the problem to get 100% on, is to just tech it up. And again, you could copy and paste from your Jupyter Lecture notebook, but it's a good idea to review how to do some tech and try to do it again on your own. It should only take hopefully like 5 to 10 minutes for you to do that, and it's good refresher on some of the tech skills that we practiced back in the 01 Jupyter Lecture notebook. Now in problem 1b, I have a function that requires some finishing touches. You are to finish it. I give you some details here in terms of what the function should have in terms of R, P naught, K, and T, right? So these are things that should be in the bullet list of explaining what's the solution to the model. And again, I would recommend coding up this version right here, this first one, that right there. That's what I would recommend coding up. It'll be much easier. This exponential function, I would recommend using the exponential function within NumPy. Since we've imported NumPy as NP, this means that you could use np.exp, and then in parentheses, you would put r times t to get the evaluation of the r times t rates to the e power using NumPy, especially if r and t are given as arrays. So you just have to finish this up. I tell you exactly what the parameters should be for this function. You just have to code up the function correctly here, and then the population values are returned. Now in problem 1c, I ask you to evaluate the function you coded with r equals 0.01, and then some other values of p naught, k, and then an array of t values, and to print the results. I ask you to repeat those computations except with an r value of 0.5 instead of 0.01. So you will keep p naught, k, and t the same values. And I want you to discuss and interpret the results in terms of the sensitivity of the population to increasing R values. So this is often what happens in computational data science, is where you code up a function or you're given a function and you start to play around with varying inputs to get a sense of how sensitive the outputs are to perturbations, changes in certain parameter values. So I'm just trying to get you used to the workflow of how this goes in practice. Now in problem 1D, I go a step further. I ask you to just run code that it works perfectly, assuming that you've coded this function so that it actually outputs a NumPy array of values as it should using this np.exp function. So if you do that, then this will generate a plot, and what you can do to check to see if your plot is correct and if you've coded this function correctly is compare it to this reference plot that I've included. So if you're not getting this result, then something went wrong, and that should hopefully allow you to figure out how to fix this until you match this result. So this is in a Markdown cell. This is a figure that you will need to upload with the notebook so that this renders properly in the Markdown cell. And it's useful to just compare what the output is when you run this code cell to make sure you got it right. And then I ask you to, again, to provide some discussion and interpretation here. And that's involving just what you're seeing in terms of the different R and K values here. So we're changing R and K values so that you could compare these plots and see what's going on. And what I'm allowing you to do is, even if something went wrong and you have trouble figuring it out in time for the submission, by giving you the reference plot, hopefully you're able to correctly interpret what's going on with different R and K values in terms of the impact on the population output over time by giving you this reference figure. So that's the first problem. Hopefully that one doesn't take too long. And then before we get to the second problem, I actually have a good amount of material for you to read as a preamble to the second problem. And it is on RBFs, which is short for radial basis functions. So I provide a link here that you might find useful to click on. It takes you to the Wikipedia article on radial basis function. In fact, you'll want to reference this because some particular examples are given and I ask you to deal with coding of 2 of them. But before we get into what are, to the actual problem, I want to explain to you why RBFs are so important in computational and data science. So they're really important in non-parametric density estimation and statistics. They're useful in approximation of function responses on unstructured data sets. And they're also useful in defining some types of artificial neural networks. Basically, they're kind of a big deal. So what is the idea, purpose, or features of an RBF? Well, I'm summarizing the big picture here, and I also provide a graph here to explain some of the take-home messages. So as a big picture, the idea is that if we have some information about what happens at a point in a space, call that point C, and we want to use this information to infer what may happen at a point X, then what we do with RBFs is the following. If X is, let's say, close to C, then the knowledge we have about what happens at C should play a big role in informing what we think may happen at X. That seems reasonable enough. If X is far away from C, then perhaps we should reduce how much we rely on the knowledge we have at C to inform us about what may happen at X. Again, that seems reasonable enough, and RBFs are things that are functions that exhibit features that codify that type of concept. This is what we would like to have happen. So how do you go from that concept to practice? Well, a few things have to be made more concrete first. What types of functions exhibit such desirable features? What do we mean by close and far away? And how do we measure distance anyway? So we make this mathematically precise with the following notation. We'll let phi, that's the Greek letter phi, denote an RBF that maps a distance r. So distance is non-negative. It can be 0 if x and c, for instance, are the same point. And it can get arbitrarily large. Phi of 0 should be the maximum, and phi of r1 should be greater than phi of r2 whenever r2 is greater than r1. So if we let C denote some point in a vector space at which we quote-unquote know something, we have to ask ourselves first, well, what is a vector space? Simple examples are R2 and R3, and well, even the real line. All of these standard Euclidean spaces where you're used to probably graphing functions or making sketches of solids in R3, these types of spaces are this very simple types of vector spaces. If we let x denote some other point in the vector space where we would like to infer something, then we let r equal the norm of the difference between these two vectors x and c. And you have to ask yourself, well, what is a norm? We'll get some practice into defining it, but basically in the context of this class, you can think of a norm as determining the length of a vector, which is simply stating how far the point defined by its coordinates are from the origin. That might seem confusing if you haven't had linear algebra before. If you haven't, just think of x and c as coordinates, take the difference in the coordinates, and then you're just determining the length of the straight line distance between the 2 points. That's all this is computing. Now, what's nice is graphically, it's quite simple to show. I'm going to have to shrink it. There we go, so I can fit this all on my screen. Here's what a Gaussian RBF looks like. Again, on the RBF here, here's that Gaussian. So it's a really simple function. You could use your exponential function in NumPy to just raise it to the negative epsilon times r raised to the second power. And you could ask yourself, well, all right, what does a function like that look like? Well, here's what a function like that looks like with different values of epsilon. Epsilon is what's called a shape parameter. And small values of epsilon make the Gaussian very flat, and larger values make it very narrow. And what we have with our phi of r for some fixed epsilon value is at a point C, we would say that's where it's maximum. And if we picked a point X somewhere else, and we took r to be the distance between x and c, then evaluating phi of r, that would be phi of this value right here, it would get a value down here. And you see that value is much less than the value here. So if x gets closer to c, phi of r will become closer to the value of phi here, which is 1, where it's maximum. And as x gets farther away from c, the r value increases and phi of r decreases and asymptotically approaches 0. That's basically what's going on with the RBF. But we should talk a little bit more about norms. So I will enlarge my font there. There we go. How do we compute R to begin with when these are in higher dimensional spaces and not just the real line? What does this notation of being a norm even mean? In one dimension, it's actually quite simple. It is just given by the absolute value of the difference between the points x and c. So let's say if c was, here it's a little less than 2 and x is around, let's say 3.5, you just subtract the two values, take the absolute value, and that's R. That's all there is to it. But we have to be a bit more thoughtful as we move into higher dimensional spaces, because there are more options available for how we would measure the size of vectors and thus the distance between points. In many cases, it is fine to simply think of this as the quote-unquote straight line distance between 2 points that you are probably familiar with in 2 and 3-dimensional spaces. But there are other useful ways of measuring distances that you should be aware of. The interested reader, or student in this case, is encouraged to examine the following resources for more information. So you can click on these links and look at various ways in which we might compute the distance between 2 points. The Euclidean distance is simply the straight line distance, and there's a way to generalize it to any finite dimension, where k could be even 10, 20, or 1,000. The taxicab distance is useful when the distance measured in moving from one point to another is best described by moving along a grid of roads. This is closely related to how we actually think of the quote-unquote real distance of 2 points on a map when the straight line path is impossible to traverse. This is sometimes called the one norm distance. So this might also be what you would think of if you're walking in downtown in a city and you have to follow the sidewalks. You're not scaling and leaping over buildings in order to get from one point to another. So you move in these straight lines that are along, you could say, coordinate axes, but you don't move in the straight line distance. It's a piecewise distance. So you can click on these links for more information. And then there's the Chebyshev distance. And this is useful when the distance measured is in moving from one point to another is best described by the longest distance we have to travel in any one direction. This is sometimes called the infinity norm distance. So we'll primarily just focus on these, the 2 norm distance, which is the Euclidean one, the 1 norm distance, which is also called taxicab, and the infinity norm distance, which is Chebyshev. Now, you don't actually have to know how to compute any of these by hand. They're fairly simple to compute by hand for low dimensions, and you could do some by hand to practice to see if your computations match or your intuition matches what the output will give you. What's nice is that in NumPy, since it has a linear algebra subpackage, that comes with a function called norm. And in that norm function, you can give it an array, a NumPy array, or in combinations of NumPy arrays, and then you can ask it to take the norm of those arrays. And you can feed it a parameter value, ord, for the order of the norm. And ord equals 2 means you are using the 2 norm. Ord equals 1 means you are using the 1 norm. And ord equals np.inf means you are using the infinity norm. So that's related to these 3 norms. So if you run this, so now we've imported norm from the lin algebra package. And let's say I take arrays A, which is 5, 5. So you could think of the point 5, 5. And B is something in 3D. It's 3, 7, 2. So it's the point, 3 on the x-axis, z in the y-axis, and 2 in the z-axis if you think of plotting in 3D in the standard XYZ coordinate frame. So now I've made these arrays, A, 5, 5, and 3, 7, 2. Now here, you could think of these as the points C here. And now I want to compute the distance of x to these various points, except instead of C, I made it A and B. Now x, initially I'm making the array 2, 3. And then I want to see what's the norm of x minus a if I pass no ord parameter. Well, as the code comment shows you, the 2 norm is the default. So another way to do that, if you just want to be really clear in your coding, if you don't want to rely on default values and be very explicit, you just pass ord equals 2. Then there's ord equals 1 and ord equals np.inf. Now, before we compute this, let's just talk about it real quickly. If you were to do this by hand, I suggest taking a piece of paper and drawing on a coordinate axis where the point 23 is, where the point 55 is, and then computing the straight line distance, connect with a straight line the point 23 to the point 55. And then you would find that you would take the square root of 5 minus 2 squared, which would be 3 squared, plus 5 minus 3 squared, which would be 2 squared. So you'd have 3 squared, which is 9, 2 squared, which is 4, and 9 plus 4 is 13. The square root of 13 should be what the output of this is and what the output of this is. So let's just go ahead and run that, and then we'll come back to ord equals 1 and make sure these things check out. So we see 3.6 now, 3.605. What is NP? Let's take the square root of 13. Takes a second to compute. There we go. That's exactly what the output is. So this is just something to help build intuition. Now, ord equals 1 is 5, and ord equals inf is 3. So let's just talk about those real quickly to hopefully make this more clear. If you look at the coordinate 2, 3 and the coordinate 5, 5 in the standard Euclidean plane, the standard plane you plot functions in, then if you take 5 minus 2, that's how far you have to travel in the x direction, and that's 3. And then to travel in the y direction to get up to the point, it's 5 minus 3, which is 2. So 3 plus 2 is 5, which is exactly what this output is with the 1 norm. And the infinity norm says the longest distance you had to travel in any one direction was 3, which was along the x direction. Now, I highly encourage you to make some of your own examples, change x around, and see if you can compute or guess what the outputs of these should be if you changed what x is. So you might just copy the contents of this code cell, put in a new code cell, maybe a few, and then just try different x values and see if you can guess what the outputs are or compute them correctly. That's something I highly encourage you to do. Then I also do this in 3D just to show you that there's nothing else to be done. B is a vector in a three-dimensional space, and now I've made x a three-dimensional vector. There we go, I'll fix that. And again, you could do the same thing. And if B was a 10-dimensional vector, I would have to make x a 10-dimensional vector. The dimensions of those two are going to have to match. And all of these computations would then give the distance in that, let's say, 10-dimensional space between these points, x and b, these vectors. So now we can talk about problem 2, which involves radial basis functions. So problem 2a is to read the Wikipedia page on RBFs, at least as far as this initial description, which just describes how important they are and some of the notation which I described above, and then really look at these examples. Because what's important, what I ask you to do here, is to summarize the following RBFs in the markdown cell below: Gaussian and bump function. That is the Gaussian function here, and the bump function is right here. So you need to tech these up, so there's more practice with teching here. And within each of those, you should say what epsilon is in terms of a shape parameter and describing this, what its role is. So we already kind of talked about that in this video, but your answers to that go here. So again, I'm just going to put this as 2 bullet points so that you don't miss it. And there we go. That's what the instructions are. Oops, scrolled up. You need to explain what the Gaussian and bump function are, excuse me, and briefly explain the role of the shape parameter. So after you've done your markdown cell on these RBFs, you will be asked to do some things in the following code cells. You should create 3 functions: my Gaussian, my bump, and a wrapper function called my RBFs. And the wrapper function is one that will choose which of these 2 RBFs, the my Gaussian and my bump, should be evaluated based on a string argument, which RBF that defaults to the Gaussian RBF. All 3 of these functions should also take in as arguments the following: x and c, which both should be numpy arrays of the same size, the shape parameter that we call EPS, EPS in the code short for epsilon, and ORD, which determines the norm used to compute the distance r between x and c. And that's just going to use the norm function in NumPy lineage that was shown before that we imported above. The function should return the value of the RBF at the computed r value. Now I get you started on the myGaussian and myRBFs function, which is the wrapper function below, but they do need to be completed. You need to write the myBump function in its entirety. So the code for the myGaussian function goes here. Notice it has x and c and eps and ORD, which is defaulted to none, and the eps value is defaulted to 1 here. R is computed by taking the norm of the distance, so it's of x minus c, so it's taking the distance from x minus c, and the ORD parameter that's given is either defaulted to none, in which case the default is the Euclidean 2 norm, but you could also, if you passed a different value here, it would get used here. So that part of the code is completed. What you need to do is compute the Gaussian RBF with shape parameter below, right here. This is the line of code. It's just one line of code that you need to finish. And again, you can come here and see I'm basically asking you to code this. It is not that complicated, but be careful with parentheses. Make sure you're taking the exponential of epsilon times r, which is itself raised to the second power, and that's what you're taking the exponential of, is the negative of that. So you have to make sure you're computing that correctly, but then that's all you really have to code on this problem. Now the code for your bump function that you're asked to compute has some logic to it, so you're going to need to code that, and you can see the exponential function you're asked to compute here. So it's a little bit more complicated, but it's not terribly so. And then the code for the myRBFs goes here, and all that should happen, what you need to fill in, are these 2 lines of code. So this is how a wrapper function, a simple version of it, works. So you could just have a function that you call that is wrapped around a bunch of different RBF functions. In this case, we're wrapping it around 2 other ones. And then you could just give it x and c, and then if nothing else, it would go call the Gaussian one. But you could say, well, no, I also want to see it with the bump function, or I want to see with these different epsilon and ORD parameters, and pass it a keyword to say which bump function, or excuse me, which RBF to compute. And you can imagine having many RBFs. In fact, right, there's many options here. And if you want, I certainly encourage you to code up a few others, perhaps the multi-quadratic, the inverse quadratic, and the inverse multi-quadratic. These might all be good ones to compute. You could even do the polyharmonic spline if you wanted to. And you might even want to create plots involving what these give as outputs. That's up to you. You can always take these things further than what I'm asking you to do, and I highly encourage you to do that. But after you do that, in order to see that it worked correctly, all you have to do is execute the code cells below to verify that both RBFs can be evaluated for the given points and vectors in the real line, R2 and R10, a 10-dimensional space. And here I'm doing different values of the ORD and epsilon parameters. So I'm going to be running this when I grade as your notebook. And so I just have these arrays, and then the point is I look if your myRBFs, your wrapper function, is working correctly, and I know what the outputs should be, but I'm basically, even if your outputs are wrong here, the point is you get the credit for this part of the problem, assuming that you've written this correctly enough that this at least executes. Now, these functions are in some sense simple enough that you could compute them by hand or with a calculator to verify some of the outputs for yourself. But I am just going to check that this is all running, and as long as all of these parts run with no error, you get 100% for the part C. The correctness of this code is judged independently by itself, but hopefully there's a way for you to figure out how to test if they're correct on your own using some simple inputs for you to verify that the outputs are correct. We then move on to the final part of the assignment, which then looks at using Doctest in a variety of ways. So I have a preamble to this problem, and it talks about the value of doing testing. So Doctest is probably the most useful to review after seeing a simple example, the documentation for it, which you can click here. There are other Python modules available for testing your code, such as unit test, but we will primarily focus on Doctest for its simplicity in this course. So here I describe the value of testing, and I don't want to necessarily read all of this to you. I've read enough, but testing is very important. I really encourage you to read this very carefully and spend some time thinking about this, especially the idea of the purpose of a doc test versus a unit test. And I also just give a suggestion where you should probably spend 15 to 20 minutes just reading more about testing and why it is useful. There are lots of blogs and articles written about unit testing, and you can find some on Google or whatever your favorite search engine is. And there's actually a nice discussion about the built-in Python modules, Doctest and unit test on Stack Overflow. But without further ado, we're just going to dive into it. We are going to run the code cells below, and you are to interpret what is happening in the markdown cell that follows. To truly understand what is happening, you may need or want to try editing the tests so that they fail. Add new test for yourself and play around with it. So here I import Doctest. Now, here I have a function defined as AB. Here I have a doc string, right? Now, while it's a rather simple function, A plus B, the point is to illustrate Doctest. So you usually, in a good doc string, you have some explanation of what the function's doing in the inputs and outputs. And then what I show are actual tests. And they're written as shown, where I have these 3 arrows, and I'm showing how the add function of 2 and 2 should return 4. And if I add 3 and 5, it should return 8. And if I add 105.5 to 0.5, it should return 106.0. Now, if I run this, now these tests are in there. If I run test mod with verbose equals true, here's the output. And you see that it's trying the 3 different tests. It's telling me that what the value it's expecting based on the output I gave it. And then it's saying whether or not it was okay. It's saying, yes, that worked. And then it tells me how many tests passed and how many tests failed. If I run it without that verbose equals true, I get this, which is a very terse output compared to what this is. So with that in mind, I also give you add strings. So this turns the parameters A and B into strings and puts them together. So now adding 2 and 2 with the add strings function should give you an output string of 2, 2 because it's concatenation. Notice I'm using the add function here. I'm taking this add function, but instead of assuming that I'm passing it just numbers, I am now passing it strings. So I run that, and now if I have the verbose equals true, you will see that the add function tests are running and also the add string tests are running. And then I see 6 passed and 0 failed. And here I also am running something else where I give it a specific function. So it's just running them on add strings. This is what run docstring examples does. I have some other parameters here. These are things for you to read about, look at, and then just understand how things are working. So this is not a graded part of the assignment, but you should really try to explain and interpret the above code cells here for your own benefit. And just in case you did not experiment with a failed test, I give you one where of test fails here. And I really say you should try to explain the results here as well. So all of this is a preamble. I'll just run this so you can see. So this test failed example. And it says exactly what failed. And you should try to explain this. And there's some stuff to read here and think about. This is a useful preamble for you to spend maybe 30 minutes looking at, reading these examples, and seeing what's going on and explaining things in your own words. And then what I ask you to do in problem 3 is actually quite short. I want you to revisit the population model from problem 1. I want you to copy and paste the solution function from your part B of that problem in this code cell here. But I also want you to add a doc string to describe the function, its parameters and outputs, and add at least 2 tests in the doc string based on easily computed inputs. And then you should use Doctest to test your function. And you should be writing tests that pass because you should be writing the function correctly and the test correctly. testing the differences module from the lecture is problem 4. I ask you to run this code cell below. This imports the differences module that we saw from the third module in this course. I also include it here, and you need to upload it and have it in the same folder as this notebook for this part to work correctly. And you'll notice that 0 tests failed. There were 2 that were attempted for diff. If you look inside of this, so I need to go to the right directory, so just give me 1 second. Here we go. Here's my differences module. So in my differences module, you notice there's 2 tests for the forward difference function. I had a docstring there. It's always been there since the third module. But I don't have any docstrings or doctests for backdiff or centdiff. And what I ask you to do is add docstrings with useful tests. So you need to add docstrings and also useful tests to every function in the module, which really just means these 2 functions here. While this computes a forward difference, this is a backward difference and a center difference. And then you should look at this computation, and you should be able to figure out by hand, maybe even using a variant of what I was doing here, what the useful test should be. And notice I'm using lambda functions in these tests. So then you need to show that all your tests pass. And so that's stuff that you have to fill in here. And then you also need to upload your differences module with this notebook as part of the assignment. And then also for the 5th problem, you are to test your module that you created from the lecture notebook. This was the one at the end of the Part C lecture notebook. So you need to create some docstrings with test for each function in that module you created as an activity at the end of the Part C lecture notebook, and then show that your tests pass. And again, that should hopefully be quick for you to develop and do. So even though there's these 3 problems at the end of this assignment, I don't think they necessarily should take that long, or at least I hope they don't. But if you have any problems, please post your questions to Canvas and I'll be there to help. So that's it. Thank you for listening. I hope this video helps make this assignment go smoothly for you.